in all fiber optics communication system, the source is either LED or injection laser. So these two are important optoelectronic source for our communication purpose, or maybe for any other types of designing of lighting technology, or others, maybe in sensing device through optical sensor. So this can be used either LED or laser diode. So here also in case of PN junction device, this LED and laser diode is equally important. In case of small distance or in low communication system, distance in terms of distance, if it is small distance or length of the optical fiber is less, then LED is useful. But in case of communication over a large distance through fiber optic link, then it is better to use laser diode, because you know that injection laser diode has more power, as well as it has high monochromaticity and unidirectional property compared to LED, right? That is why for long haul communication, injection laser is better. But in case of short communication, that is the length of the fiber is small, then it is possible to use LED. Now, first we consider the characteristics of LED. LED basically a PN junction device that emits spontaneous radiation in ultraviolet region, or in visible region, or in infrared region, depending on the material is being used and its band gap energy. And the emitted photon energy is not exactly equal to its band gap energy, but somehow it is relatively greater energy of the band gap energy is emitted. Now the output photon energy that can be expressed mathematically by the equation, that is I, this output in terms of, if we consider the energy of the photon, then intensity will be like this, that energy of the emitted photon is this EPH, that is equal to A some constant multiplied by root of EPH minus EG, that is to the power half, that's mean root e to the power minus EPH minus EG divided by K. So this is the emission spectra, and this emission spectra has peak at photon energy nearly equal to Eg plus KT. But it can be, apparently it can be seen that the maximum peak will appear at Eg, but no, it will appear at Eg plus KT. KT is the due to the thermal agitation in different level of carrier in conduction band for electron and valence band in whole, it is appear. And the full width half maxima intensity will be 2.4 KT. This is experimentally observed phenomena. Now, the relative intensity is this. If we plot with respect to energy, emitted photon energy, then below the Eg, no photon will be emitted. And above Eg, then it will start to emit, and the peak value is maximum at Eg plus KT. Then it is decay continuously, right? So in terms of photon energy, in terms of emitted wavelength, then it will be peak at certain this wavelength region, corresponding wavelength region, that is lambda, and there is a spreading over lambda, that delta lambda, that is full width at half maxima, half intensity maxima, that can be lambda equal to hc divided by EPH. hc divided by EPH, that can be calculated delta lambda, that is equal to minus hc divided by EPH square delta EPH. That is the spreading of photon energy. The line width of output spectrum of LED is second figure, and next we consider the efficiency. Now, after absorbing this, due to this apply voltage and current, it will radiative and non-radiative both type of recombination will takes place. Only the radiative recombination can produce light, and in radiative recombination, that emitted light may also absorbed by the material itself, then it cannot release from the diode, and it can be internally absorbed, right? But if we consider the absorbed there is no absorption of the radiated photon. If the radiated photon will escape from the diode, then we consider two types of recombination, that is radiative recombination and non-radiative recombination. So now if we consider the lifetime of radiative recombination is tau Rr, and lifetime of non-radiative recombination is tau Nr, then we can write the internal quantum efficiency. Internal quantum efficiency, that will be 1 divided by tau Rr divided by 1 divided by tau Rr plus 1 divided by tau Nr, where tau Rr is the radiative recombination. That means that recombination contribute in photon. But in case of non-radiative recombination, it will not contribute in photon, right? Therefore, this is the internal efficiency, but internal efficiency is not equal to the external efficiency. That means this photon will radiate, but all the radiated or emitted light will not appear in the outside for coupling to the fiber, because that radiated photon energy, that means light, may be absorbed by the material which is being used to produce the diode. So that material can also absorb this light. So in that situation, if we consider the absorption factor, if AS is the fraction of light absorbed within the semiconductor material, and mu s and mu a are the refractive index of the semiconductor and the surrounding mediums, then the external quantum efficiency, that will be internal quantum efficiency minus 1 minus as. 1 minus as means as is the absorption coefficient. So radiative coefficient of that material is 1 minus as multiplied by twice mu a cube divided by mu s into mu s plus mu a whole square. That mu s is the refractive index of the semiconductor material. That means the material of the diode, and mu a is the material of the external maybe air, maybe LED material, whatever may be when it is coupling. So then LED, or it may be intermediate some material in between LED and fiber. that may also takes place. That is the refractive index mu A. So external quantum efficiency that can be treated as like this: eta internal multiplied by 1 minus as into twice mu A q divided by mu s into mu s plus mu A. In other words, we can say the external quantum efficiency is equal to the output power divided by input power. External quantum efficiency that can be calculated in terms of output power divided by input power. So output power means optical output power, and input powers means the multiplication of current and voltage. That is current applied in the diode, voltage applied in the diode, and the corresponding current, right? So IV, so external efficiency, quantum efficiency, that can be treated as P out divided by I into V, and if we consider it is in percentage, then multiply it by 100. The external quantum efficiency of an LED using indirect bandgap semiconductor material is generally less than 1%, right? So if we consider the indirect bandgap semiconductor, then this external quantum efficiency is less than 1%, whereas for direct bandgap semiconductor, it can be substantially high. Now, after getting this quantum efficiency, we need to couple this optical power for fruitful application in optical communication, in sensing application, or any other application, or in case of lighting technology also. The coupling mechanism, optical power from LED to optical fiber, are different for different types of LED and fiber. So if different types of fiber and different types of LED, the coupling mechanism is different. Generally, some lens is being used for coupling, or some index matching fluid is also used, or index matching material that can be used in between LED and fiber, and also some external parameter can have some important role, that is numerical aperture, fiber material. This can have some important role for coupling the optical power. The power coupled into a multimode step index fiber from a surface emitting LED, that we can consider both surface emitting and edge emitting. So if it is surface emitting LED, then coupled power or optical power coupled to the fiber, that POF, that is equal to pi 1 minus r Na square divided by P out, where P out is the output power of the LED, Na is the numerical aperture of the fiber, and R is the Fresnel reflection coefficient of the fiber surface, in which surface it is coupled. That surface or that material has the reflection coefficient R, so absorption coefficient will be 1 minus R. So the coupled power in the fiber will be pi into 1 minus R numerical aperture square into P out. So this is the coupled power in the optical fiber. Now this LED material basically direct bandgap semiconductor material is being used for design of LED. Basically for LED application, direct bandgap semiconductor material is being used. But I have already mentioned, if it is indirect bandgap semiconductor material, then it is efficiency is less than 1%. So which is not effective. So direct bandgap semiconductor material are basically used. Actually, the LED, blue and white, these two light before 1990, other LED, that is red, green, or other LED is available, but blue LED was not available before 1990. In 1990, for material that is uh, gallium nitride, indium gallium nitride, or zinc selenide, this material, semiconductor material, has been used to design the blue LED. So when blue LED has been discovered, or this three-person has been discovered, I cannot remember their name, but after 1990, they discovered the blue LED, and based on their discovery in 1914, they have got the Nobel Prize on that. So this blue LED makes a revolutionary change in the lighting technology, because this red, blue, green can produce the white light LED that was produced. The first huge importance for blue LED, and that has been possible due to the availability or for proper designing of gallium nitride, indium gallium nitride, or zinc selenide, this semiconductor material, right? Then blue light as well as white light LED is available commercially, and based on that, by color combination or by this, they have designed the LED, that is blue, green, and red combined. By color mixing, they design the white light LED, or blue and yellow, yellow phosphorus, that can be combined to form the white light LED. Then in the commercial market, after that, the white light LED will came, and then in lighting technology or for decoration purpose, there are white LED is being used. Now this LED basic structure, that is surface emitting and edge emitting LED, we are not interested to discuss detail the surface or edge emitting LED, but you can see from books that reference I have given. Now basically this LED I have already mentioned that mainly used for optical communication, for short hole communication or short distance communication in the wavelength range of 0.8 to 0.9 micrometer. And this is gallium arsenide or gallium indium arsenide is being used material, and indium phosphide, gallium indium arsenide phosphide is also used for LED application for optical range 0.93 to 1.65 micrometer range, and this can be coupled with the optical fiber by using some index matching liquid or index matching fluid, that may be epoxy resin or lens or graded index rod lens, that can be used for matching the refractive index or to couple the light from LED to fiber, that can be used. And it has many applications like optical sensor, lighting technology, for decoration, display devices, LED devices, display. This can be also done by using LED. So this is I have already mentioned, this is surface emitting LED. That means these are the different material. This is the substrate material on which it will be high refractive index material that will produce the LED, light emitting, and that emitted light will be confined within a particular region. Then after a particular threshold value, then it will escape, and from surface or from edge it can be done, and this can be considered as surface emitting LED, and this is the edge emitting LED. So the intensity of light will emit through the edge of this device, That's mean here refractive index has been changed, and then it will escape through this, and in other region it will be shielded by proper considering the refractive index of the material. Then for coupling, in case of fiber, the coupling can be done by different technique that I have already mentioned. এই ফোন এসছে সোনালি, দেখো। So this is a multi-mode fiber, and this fiber it is coupled, that is surface emitting LED. So these are the active region, like your laser active region, we can say this region will effective for producing the light, and that light can be coupled to the fiber, and this fiber has already been coupled within this core by some epoxy resin, this material, which will match the indexing so that the maximum light will be coupled to the fiber, right? So this is surface emitting LED, which is coupled to multimode fiber with the help of epoxy resin. Now you see another, that is edge emitting LED. When this edge emitting LED, it will emit the radiation, then we have used, that is green rod lens. Green rod graded, here I have mentioned graded index rod lens, and that will match the refractive indices of between these two regions so that it can be coupled the maximum emitted light to the fiber core in single mode fiber. In single mode fiber, when it is coupled, then this will be applicable for relatively long haul communication. Relatively long haul communication can be done by single mode fiber, that you know. So for that purpose, it will be coupled by using the green rod lens, and it can be used for this communication purposes. Now the detailed structural description of surface emitting LED and edge emitting LED that I have mentioned in these references, fiber optics and optoelectronics, Oxford University, that is R.P. Khare. You can see, or you can follow these books for to read this. Okay, and now we come to the problem. Can you understand?
Yes, sir.
Yes, sir.
So now we come to the problem. I have given here two problem, and I have also solved it. First problem is the internal quantum efficiency of a gallium arsenide LED is 49%. The emitted energy of the photon is 1.42 eV. When the voltage drop across the LED is 1.5 volt and current is 100 milliampere passes through it. If the LED output is coupled into a step index fiber core and cladding refractive index 1.65 and 1.48 respectively in air medium, then calculate the launched power into the fiber and the optical loss in dB. You have to calculate the power launch in the optical fiber and optical loss in dB. The self-absorption coefficient and refractive index of the LED material are given. So you know the external quantum efficiency of gallium arsenide LED, eta external, that is eta internal 1 minus AS multiplied by twice mu AQ divided by AS mu S plus mu A whole square. This is whole square. I have forgotten here perhaps. So this is whole square. So this is quantum efficiency, it is 49%, that is 0.49 into 1 minus 0.1, 0.1 AS refractive index, that is 0.1 in the surrounding refractive index 0.1, then mu A refractive index or refractive index 1.6 and one core. Oh, sorry, it is in air. So that is why I have taken mu a equal to 1, 2 into 1. Then mu s is 3.3. It is given 3.3 plus 1. So after calculating, maybe my calculation may be wrong because I have not given here square. It is a square term. If you see here, it is a square. So if you make it square, this is my, I have forgotten. So after squaring, then you will get the result, that is external efficiency, right? Then the numerical aperture of the fiber you can calculate because refractive index of the fiber is given, and the LED source fiber coupling coefficient, that is source to fiber coupling coefficient, that is eta external numerical aperture divided by square. That I have not discussed here. So this is the source coupling coefficient. This can be this. So if you calculate like this, then the power launch into the fiber, launch power will be eta this I divided by EPH. So this current I have already mentioned, charge, that is and photon energy, that we have already mentioned 1.42 ev, 1.42 ev. So in terms of E, if we multiply, then it will be cancel out, so it will be milliwatt power. And at the same time the input power is 1.5 into 100, so 150 milliwatt. So therefore the overall power coupling efficiency, that is output power divided by input power, so this is the efficiency. And in terms of optical loss, if we calculate, that is minus 10 log this efficiency, then it will gives you 15 dB. So it is the loss, optical loss is this, and this is the coupling efficiency. Point is clear? Then another problem, a surface emitting LED produces an output of 80 milliwatt when it is connected to a DC voltage source of 5 volt and across a resistance R. It is found that the current through the circuit is 100 milliampere and the voltage drop across LED is 1.5 volt. What is the output efficiency of the LED and the value of the series resistance R? Which resistance 1/4 watt or half watt we will be preferred for this circuit. Now the output efficiency of the LED is eta, that is equal to 80 milliwatt divided by voltage into current, that is 0.53, that is 53%. The value of the series resistance R will be voltage drop, it is 5 volt supply and across the LED is 1.5 volt, so remaining drop will takes place within the resistor and it will produce 1.1 ampere current. So the resistance is 35 ohm. The voltage drop across the series resistance is 3.5 volt. So the power rating of the resistor is 3.5 volt into 100 milliampere. So 350 milliwatt. 350 milliwatt. Thus 1/4 resistance will burn out. Right? So that means if the resistor will consume the power of 350 milliwatt, then if it is 1/4 watt, then that resistance will be burned out and circuit will be damaged. So that is why you must use half watt resistance for this purpose. Can you understand?
Yes, sir.
Yes, sir.
Okay. So I will stop it here, and next I will share this note to you, And one more thing, that as per schedule, that from 26th December your examination will start. Your final examination will start from 26th December. So before that, perhaps I have two more classes, right? So I have two more classes. So this unit 2, I will finish it here. Another topic that I will not discuss in detail, that I will mention, that like LED laser diode can also be used for optical source, right? So we will not discuss in detail of that laser source.
Sir, sir, I had a question, sir. Sir, there were
Yes,
a couple of formulas that you used in the problem, sir, which were not in the notes, sir. So, where will we get those from, sir?
that formula I have mentioned in the problem. Only one formula has been used in the problem that I have written in the
Okay, sir.
problem. That is why I have solved the problem,
Okay,
right?
okay, sir.
For
Okay, sir.
this reason, I have solved the problem.
Okay,
So
sir.
don't worry about that. Which formula is available to you within the note or within the problem, that you prepare yourself. Okay.
Okay, sir.
Or for your own interest, that is the description or the structure of surface emitting and edge emitting, you can see any book you can see. Okay, so these are the things. So I have remaining two classes, next Monday and Monday to next Monday, right? So these two classes we will discuss the unit 6, that is VLSI, integrated circuit, that is basically the memory circuit. So we will discuss next two classes for memory circuit. So this unit 2 I will stop it here. Point is clear?
Yes, sir.
Okay.
Yes, sir.
Okay, so next two classes I will discuss unit 6, that is basically the memory circuit we will consider. And after that I don't have any class, then it will be examination. From 26 your examination will start. Okay. Okay, so you can